Hello, good afternoon everybody. So we are continuing our discussion on neutrino electromagnetic properties, and this lecture will be devoted to the theory of some new effects in neutrino spin and spin flavor oscillations in magnetic field, in other configurations of electromagnetic fields, and also accounting for the effect of matter, which we suppose can move. So this is the subtitle: Neutrino spin and spin flavor oscillations in magnetic fields and moving matter. And this is a visual image of what I am going to present. So we are considering transitions, mixing and oscillations between left-handed neutrino and the right-handed neutrino. Also, we shall account the possibility that in this transition the type of neutrino is changing. So electron neutrino is converted to the muon neutrino and vice versa. And we, in addition to the effect of the arbitrary electromagnetic field that is described by the electromagnetic field tensor F mu, there is a medium or matter through neutrinos are propagating, and we suppose that matter is composed of different particles. And as an example, we shall consider that matter is composed of electrons, protons, neutrons. However, muons can be also included, but this is not of interest for our discussion, because muons decay, and so, and also we shall describe and account for possible polarization of each of the matter components. Here is the list of our initial papers published together with my student and postgraduate student Andrei Yegorov, and my colleague who passed away about a year ago, Andrei Lobanov. And this series of papers starting from our 3 or 4 papers in PhysLab B in the beginning of the century. So at first we considered this problem using the so-called quasi-classical description of neutrino interactions with the electromagnetic fields and moving matter. And we start with the generalization of the Barman-Michel-Telegde equation of electrodynamics for the evolution of the spin vector. And this equation is shown here in the most general form, where S is the vector of the spin vector of a neutral particle. In our case, this is a neutrino. F mu is the arbitrary electromagnetic field, and U is the four vector of neutrino velocity, speed. Beta is the 3-dimensional vector, and we suppose that beta is a constant vector. So this is the most general starting point, and we manage to generalize this equation that comes from the electrodynamics to the case when the effect of neutrino interaction with through weak interactions with the particles of background are also accounted for. So this is our main achievement in this field. Yeah. So, and what we has done. So we generalize this equation and we substitute the electromagnetic field tensor by itself plus the tensor G mu that should account for neutrino interaction with matter composed of the particle mentioned above that also can move and can be polarized. So, and the problem was how to get an exact expression for this introduced tensor G mu that accounts for neutrino interaction with the background matter. So we are following the Lorentz invariant evolution, and we have for each of the matter components, electron, neutron, and proton matter particles, we introduce the four-dimensional currents G, F runs the types of these particles, and also lambda, that is the polarization of each of these matter components. So N for different particles of the environment are the number density of these particles. V is the speed of this component of matter in the reference frame in which the mean momentum of each of these matter components is 0, and Xi is the mean value of polarization vectors of each of the matter components in the above mentioned frame. So we have 2 for each of these particles of background, 4-dimensional vectors. And from very general restrictions and demands, we can construct the following structures that can contribute to this tensor G mu that accounts for the neutrino interactions with the particles of the background. Here is the list of these different structures composed of 4-dimensional vectors U and G, and we can thus write this tensor G mu in the most general way that is shown here, and we can also express this tensor that accounts for, describes the neutrino interaction with the background matter in a way similar to the expression for the electromagnetic field tensors. We can introduce 2 3-dimensional vectors P and M that from the previous evolutions has the following form. So this substitution of the F mu electromagnetic tensor to itself plus this G mu means that we add to a real magnetic field some additional part that looks quite similar to the magnetic field, but that that accounts for interaction of neutrinos with the moving and polarized matter. In a corresponding way, the electric field is also gets additional part that is described by 3-dimensional vector P that also accounts for and acts as a kind of quasi-electric field. But these M and P are characteristics of neutrino interactions through weak interactions with particles of the environment. So, and finally, we get the following in the laboratory frame, the following generalized Barr-Michel-Telegde equation of the 3-dimensional neutrino spin vector evolution accounting for interaction of neutrinos with the magnetic and electric fields. These B0 three-dimensional vector in E0 are expressed through the vectors given in the laboratory frame. This B0, E0 are magnetic and electric fields that are seen by neutrino in its rest frame, and this following to the Lorentz transformation for the magnetic and electric fields are expressed in terms of magnetic and electric fields components determined in the laboratory frame. So the first part of this right-hand side of this equation is just a usual electromagnetic interaction of a neutral particle, in our case a neutrino, and the second part here is M0 and P0 accounts for the effect of interaction of neutrinos with the matter. So this is the generalization of the Barr-Michel-Tellig equation for the neutral particle of electrodynamics to the case when we also incorporate possible weak interactions of neutral particle, it means our neutrino, with the particles of the environment. So now we have to determine this rho and psi, and of course we should fix the theory, and we should start with the interaction, electroweak interaction Lagrangian of neutrinos with the particles of environment. This is F, four-dimensional vector in this standard model of weak interactions that is expressed in terms of the current and polarization. For simplicity, as an example, here we account only for the electron matter component. And just from this definition, introduction of neutrino interaction with the particles, with the electron of the background, we can derive the explicit forms of this ρ1 and ρ2, and if we also account for the prediction of the standard model for the neutrino magnetic moment, it's proportional to the mass of neutrino, we get the following very simple expressions for ρ1 and ρ2. And finally, we arrive to the following expression for this M0, three-dimensional vector. I would like to recall that this is in addition to the real magnetic field that is accounted by the Barr-Michel-Tellig equation. So this is an addition due to weak interactions of neutrinos with the electrons of the background. N is the invariant number density of electrons. Gamma is the Lorentz factor of neutrinos. Beta is the velocity of neutrino. Rho1, Rho2 we have just derived in the previous, and VE is the speed of electron background in the laboratory frame. Yeah, and so this is an exact expression, but here we omit terms inverse proportional to the huge value of the Lorentz factor of neutrinos. That obviously we consider in this case that neutrino is ultra-relativistic particle, so we do not show here an explicit form for this M0, but you can find in my papers the exact expression, it's possible to calculate. So just from this expression, it follows that we can reproduce the known effect of non-moving or slowly moving matter when the speed of matter component. I would like to recall that we are dealing with only one particle type of particles present in the environment, electron. When v is much less than the speed of light, we get this expression for the m that contribute to the Barman-Sheltelig generalized equation. And the first term here exactly reproduced the Wolfenstein term that was discussed many times in our previous lectures when we were considering neutrino mixing and oscillations in presence of non-moving or non-relativistic matter. And the second term here is due to possible effect of matter polarization, but now we are not interested in this, so I don't want to comment. So, and in the other case, when matter is moving with a relativistic speed, when v is very close to the speed of light, obviously less than 1, yeah, we get the following expression for this m, and we see that in the case when a matter is moving, this is a green line, in the direction of neutrino propagation, this is the red arrow, yeah? So we come to the conclusion that matter effect contribution to neutrino spin evolution equation is suppressed. So on the contrary, when matter is propagating against in the inverse direction in respect to neutrino motion, we shall get that there is effectively the huge increase of matter effect. So the conclusion here is that indeed the matter motion itself can drastically change the matter effect in neutrino spin and as well as neutrino flavor oscillations. This is very important conclusion from the studies I have just presented. So, and basing on this approach and basing on these derivations, we have formulated, applied the results to different situations, and we formulated some new effects that I am going now to discuss with you in the next part of my lecture. And the papers are shown here, right? It can be possible to read. So, first of all, now we know how to treat neutrino spin oscillations in arbitrary electromagnetic fields. So, just before these our studies, only the case of the constant magnetic field was considered when people were discussing neutrino spin or flavor or spin flavor oscillations. And the formalism that we have derived enable us to consider, for instance, neutrino mixing and oscillations in various configurations of electromagnetic fields, accounting for instance, the electromagnetic field of the field of electromagnetic wave. And in these our papers, we have considered neutrino spin and spin flavor oscillations in the presence of electromagnetic field. And we have derived a new expressions for the probabilities of oscillations in the presence of electromagnetic fields, and have found that there could be a new type of resonance that is given by this resonance condition. So we here is the matter potential, if matter is present. Delta M is the mass-weight difference. A depends on the vacuum mixing angle, on the type of transitions we are considering, whether it's neutrino spin, let's say from electron left to electron right, or spin flavor, neutrino electron left to muon right. E is the energy of neutrino, J is the polarization of electromagnetic field, and omega is the frequency of the electromagnetic field. And cosine phi is the angle between the neutrino propagation and the propagation of the electromagnetic field. So the formalism that we have developed enable us to consider for the first time neutrino spin and spin flavor oscillations in presence of electromagnetic fields and obtain the resonance condition for amplification of this kind of oscillations. This is one of the important results which we obtain in applying of the theoretical approach to the problem. So now I would like to discuss in more detail some other new effects, and I would like to recall what kind of problems can be treated with the formalism that we have just developed. So we are considering neutrino mixing and oscillations between left and right neutrinos, whether with change of type of neutrinos electron to muon, or without change electron left to electron right neutrinos. And now we shall fix our attention to the matter effect itself. So once again, I'm showing this generalization of the Barman-Shell-Telegde equation that implies the shift of electromagnetic field tensor and the adding of discussed above tensor G mu that accounts for the neutrino interaction with the background particles. Effectively, it means that there is a shift of magnetic and electric fields, and this is what we have get for the neutrino's three-dimensional spin vector evolution. So if there is a magnetic field present, the first term describes just this. It is electrodynamics interaction of neutrino with non-zero magnetic moment with the external magnetic field, and the second term here accounts for weak interactions with matter. And I would like to point here that this three-dimensional vector G that accounts for weak interactions is inverse proportional to the magnetic moment of neutrino. It means that the second term does not depend on neutrino magnetic moment. So it means that the evolution of the neutrino spin can be produced whether through weak interactions, electromagnetic interactions of neutrinos with the magnetic field through non-trivial magnetic moment of neutrino, or due to weak interactions of neutrino without need for non-zero neutrino magnetic moment. This is another very, very important result that comes from our investigations. Well, and once again, so let's consider the easiest generalization of the standard model and consider the, let's say, the electron neutrino moving in matter composed of electrons. Then the equation for the three-dimensional neutrino spin evolution reads as it's shown here. As I have mentioned, the first term here is due to weak interaction of due to electromagnetic interaction of neutrinos through non-zero magnetic moment. And I would like to recall, once we suppose that neutrino is a massive particle, even in the easier generalization of the Standard Model, inevitably neutrino has non-zero magnetic moment. Gamma is the Lorentz factor of neutrinos, and there is a second term here that also can produce the evolution of neutrino spin, m. And m is given exactly by this formula that is proportional to the matter density. N is invariant number density. Beta here is the speed of neutrino, and v is the speed of matter. And what is very important, this part, the first term here, is the longitudinal in respect to neutrino propagation contribution to this m that obviously can't produce the neutrino spin evolution. And the second term here is transversal part of m three-dimensional vector. So, and just from here it follows that neutrino spin precession, so the conversion between left to right neutrino, can be produced by a weak interaction of neutrinos with moving matter in case when the transversal current of matter is not zero, transversal to neutrino direction, propagation of direction of neutrino propagation. This is very, very important fact that was first observed in my paper about 20 years ago. So there is a study of neutrino spin evolution in presence of general external fields, not only electromagnetic fields or fields that can be described, weak interactions of neutrinos within the Standard Model. And we, in this paper, we consider the general types of non-derivative interactions of neutrino with external fields given by this Lagrangian. So we account for the scalar, pseudo-scalar, vector, axial vector, and tensor and pseudo-tensor fields and interaction of these fields with neutrinos, and obtained in the most general form relativistic quasi-classical neutrino spin evolution equation in the following form. There are different contributions of different types of fields, and from this general Barmel-Shell-Telegde equation, it follows that neither scalar nor pseudoscalar nor vector fields contribute to the spin evolution. So, and the final conclusion is that indeed only the electromagnetic interactions and Standard Model weak interactions described by this discussed above tensor G mu can contribute to neutrino spin evolution. So, in my papers published about 20 years ago, entitled Neutrino in Electromagnetic Fields and Moving Media, so I just consider for this first time the effect, the possible effect, and I predicted that it could be of mixing between neutrinos of different spin orientation, let's say electron left and electron right neutrinos, or the same effect exists in the case of electron left neutrino and muon right neutrino due to weak interactions of neutrinos in case when there is non-zero transversal matter current. And I have derived the explicit form for this probability of oscillations that is given by this very common, very simple equation, where sine squared double effective mixing angle given by this ratio when delta reads like it follows here. It depends. And also here I also include the possible effect of neutrino spin and spin flavor oscillations due to presence of non-trivial, non-zero longitudinal and transversal magnetic field components, and delta squared is given by this expression, and E effective is given by this. And just from this it follows that indeed even in the absence of magnetic field and magnetic moment, we can just set this magnetic moment of neutrino to 0. B transversal and also longitudinal can be set also to 0. And there is only one contribution to E effective due to M transversal. And M transversal is given by the second term here. And also it depends on ρ, and ρ is inverse proportional to the magnetic moment of neutrino. So it means that here this magnetic moment of neutrino cancel out with this magnetic moment in the denominator. So it means that really neutrino electron left mixing to electron right, and the corresponding oscillations exist or can be produced if neutrino is propagating in moving media, and in case when there is non-trivial, non-zero transverse matter current. This is a new phenomenon that was discussed for the first time in this my paper, and in the conclusion one reads the following: the possible emergence of neutrino spin oscillations, for example, neutrino electron left to neutrino electron right, owing to neutrino interaction with matter under the condition that there exists a non-zero transverse current component or matter polarization, is the most important new effect that follows from the investigations of neutrino spin oscillations in the section 4 of this paper. So far, it has been assumed that neutrino spin oscillations may arise only in the case where there exists a non-zero transverse magnetic field in the neutrino rest frame. So this is the formulation of the new phenomena of neutrino spin and spin flavor oscillations engaged by the neutrino weak interactions with the background matter, and this effect is produced by non-zero transversal matter component current of matter. Yeah. So this effect has been confirmed in more recent papers, and it was used in the study of neutrino helicity conversions and oscillations in different astrophysical environments. So this effect has found some application in problems of neutrino propagation in astrophysical medias. So now I would like to turn to the fourth, I suppose, new effect that has been already announced and was introduced within the quasi-classical treatment of neutrino propagation in the background media. And we call this phenomena the spin light of neutrino in matter. So neutrino moving in a dense environment, in dense matter, can emit light, and this is the diagram that shows this process, that corresponds to this process, and the coupling of the emitted spin light photon is due to neutrinos is due to possible non-trivial neutrino electromagnetic properties, in particular non-trivial non-zero neutrino magnetic moment. And this is indeed a new mechanism of electromagnetic radiation stimulated by the presence of matter, in which neutrino with non-zero magnetic moment emits light. So at first we develop the quasi-classical treatment to this phenomena, but obviously this is a quantum effect. And just to develop the quantum theory of spin light, we generalized the well-known method of exact solutions, so-called method of exact solutions in the quantum electrodynamics, to the case when neutrino is moving in the background matter. So this method implies that at first stage an exact solutions for the particle wave functions in the presence of the environment, whether in the presence of electromagnetic fields or accounting for particle interaction with the background matter, are found, and then using these wave functions, accounting for interaction with the background, particular characteristics of particular processes are calculated. So this method was developed mostly for application to the theory of cyclotron radiation. So the initial photon can emit light, and within this method of exact solutions for the initial or final electron states, we use the exact solutions for the Dirac equation in electromagnetic field. So this is a Dirac equation for neutrino, for electron wave function, accounting for interaction with the magnetic field, if we are considering the effect of the phenomena of cyclotron radiation, this radiation of light, of photons, in the magnetic field. So that was method well developed and applied to different processes in electrodynamics, accounting for the effect of external electromagnetic fields on particles. And we just generalize this method. First we apply it to neutrino moving in external electromagnetic fields, and then we generalize this for inclusion or effect of neutrino interaction with the dense environment. So we just use the method of exact solutions for neutrinos moving in not only in the presence of electromagnetic fields, but also we count within this method the effect of neutrino interaction with the particles of background environment. So this set of papers when this method was developed. And so, this method enable us to determine or just to find an exact expressions for neutrino wave functions and neutrino energies in different environments. So we can introduce the neutrino quantum states in presence of magnetic field and dense matter. And this method, method was mostly developed for the needs of the spin light of neutrino in matter. And also within this method, we have found another very interesting phenomena, that is the neutrino energy quantization in a rotating matter. So this is another new phenomena that has been predicted in the general study of neutrino propagation in dense environment. So first, let's deal with the spin light of neutrino in matter. So once again, this is the initial state of neutrino. This is a final state of neutrino. The broad lines on these Fermat diagrams indicates that we use the exact solution for neutrino wave function, accounting for the matter potential. In the series of our papers, we have found an exact solution for the neutrino wave function. This is the mass of neutrino, and F is the matter term, four-dimensional characteristics of matter that contains the matter current and matter polarization. And it is possible to find an exact solution for this equation. And within this approach, the spin light of neutrino is a quantum process in which the excited neutrino state, left-handed in neutrino state, is converted to the low-lying right-handed neutrino state with emission of the photon. And this is the papers where we have developed this quantum theory of spin light of neutrino. And within these studies, it is possible to derive the power and the rate of the spin light of neutrino matter, and also it's possible to describe the special distribution of radiation power. And we have found that there is a very strong projectile-like effect. So this is the neutrino, this is the direction of neutrino propagation. So, and all spin light is confined within the narrow angle in the direction of neutrino propagation. And of course, depending on the P here, this neutrino momentum, this is a mass, and depending on this ratio, the form of this distribution radiation is different. Yeah. Well, of course, the effect is very, very slow because the probability, the rate of this effect is proportional to the magnetic moment of neutrino squared. And here this kind of, well, for fun, we estimate when the reverse rate or characteristic time of this effect is much less than the age of the universe. And the result is that indeed for ultra-relativistic neutrinos with the momentum or energy is 10 to 20 eV, with a huge magnetic moment of neutrino of about 10 to minus 10 Bohr magnetrons is one order of magnitude bigger than the present upper bounds from the terrestrial erect experiments, and with a very dense matter and this invariant number density of particles of environment about 10 to minus to 40 cubic centimeter, we get that really this demand is fulfilled. Yeah, it follows that for this particular choice of parameters, this characteristic time or inverse rate is proportional to something 10 to minus 8 seconds. So it means that really also obviously the effect is very, very small, very, very rare, but nevertheless there are some indications that in some astrophysical extreme external conditions with the ultra-relativistic neutrinos, this effect can proceed. So in subsequent papers we account or consider the effect of plasma mass. Obviously, when there is a dense environment and photons that might be emitted by the mechanism of spin light of neutrino should get non-zero mass, and we discuss also the effect of plasma mass, and also have shown that even accounting for this effect, the process of spin light of neutrino nevertheless can proceed. And this is one of our final recent papers, published in the Journal of Cosmology and Astrophysical Physics about 7 years ago, with a very ambitious title, Spin Light of Neutrino in Astrophysical Environments. So indeed, we examine a variety of astrophysical situations when one might think about spin light of neutrino production with some hopes, but probably once this effect would be observed in real experiments. We examined different options and have found then these conditions for observability of the spin light of effect could exist in the case of short gamma ray bursts. And we just make concrete estimations with numbers and show that there are some chances to think about that this spin light of neutrino would be observed once in experiments. So now I would like to turn to astrophysical bounds on the neutrino magnetic moment. I would like to recall that indeed the magnetic moment of neutrino is the most reasonable, well accepted among possible non-trivial neutrino electromagnetic properties, because as probably you can recall that even in the easiest generalization of the standard model, once we accept, but this is a fact, that the mass of neutrino is not zero, immediately, inevitably, the magnetic moment of neutrino should be, not would be, but should be non-zero. Also, it could be very, very small if we confine ourselves to the easiest generalization of the Stern model, and if we are not including some effects of new physics. But nevertheless, even in the easiest generalization of the Stern model, the magnetic moment of neutrino is, this is a fact, confirmed experimentally, due to the fact that neutrino mass is not zero, So, and now I would like to start with the results that at first were obtained by Raffelt in 1990, and there are a series of papers published in recent years confirming that early result of Gregor Raffelt, astrophysical bound on effective magnetic moment. And what was the idea of this paper? Once magnetic moment of neutrino is not zero, due to the plasmon decay to neutrino-antineutrino pair, the effect of cooling of radiant stars can be modified, and Raffelt calculate this plasmon decay due to this plasmon is coupled to neutrino through non-trivial neutrino magnetic moment. Here is the expression for the neutrino magnetic moment squared that has contributions from diagonal and off-diagonal magnetic moments for the mass states of neutrino, as well as there is a corresponding contribution, might be corresponding contributions from the electric dipole moments of neutrinos. And using this Lagrangian, accounting for the magnetic moment and electric moment interaction with neutrino fields, the decay rate obtained in the following way. And this new magnetic moment plasmon decay process enhances or violates the standard model photoneutrino cooling of the star by proton polarization tensor. This is a diagram shown here. This is a standard model contribution. And as a result, more fast cooling of the star could appear, and in order not to be in contradictions with the observational data, Raffelt obtained that the magnetic moment should be not bigger than 3 × 10⁻12 Bohr magnetrons. This is indeed the best astrophysical limit on neutrino effective magnetic moment, and this result has been repeated with the more fine and more tiny calculations of different aspects of this phenomena, but nevertheless the limit remains just on the same order, something maybe less than 3 × 10⁻12 Bohr magnetrons. Well, there is another possibility to incorporate the effect of non-trivial neutrino magnetic moment in different astrophysical situations, and as a consequence, again, another type of constraints, astrophysical constraints on magnetic moments of neutrinos can be set. Well, and here I just listed 3 phenomena that provide or can provide the astrophysical limits on the neutrino magnetic moment. First of all, if the magnetic moment is not zero, then the helicity change in neutrino magnetic moment scattering on particles of environment, on electrons as well as protons and neutrons, provide the transition between active left-handed to sterile right-handed neutrino. Then there is another type of transition between left and right-handed neutrino, that effect that can proceed if there is a transversal magnetic field in the environment, and through the spin or spin flavor precession or oscillations, this transition between left and right neutrinos can proceed. And the third possibility that we have already just discussed of neutrino left to right conversion in the process of spin or spin flavor precession in the transversal matter currents or matter polarization. There are 3 different types of processes that can result in neutrino left to right transitions, and that is very important from the point of view of astrophysics, because the left-handed neutrinos are active, interacting with the background particles, while the right-handed neutrinos are nearly completely sterile neutrinos. So there is a quite different behavior when these type of neutrinos, left and right-handed, are propagating in the environment. So, and these effects can be used to constrain the magnetic moment. However, the third one, the neutrino left to right transition, does not depend, as we have just shown a couple of minutes ago, does not contain any information of, is independent of neutrino magnetic moment. But nevertheless, this effect also provides the transition between left and right-handed neutrinos. And this phenomena applying to concrete astrophysical settings, in particular to the experimental data on the supernova 1987A neutrinos, just provide the following upper bound for neutrino magnetic moment on the level 10⁻12 Bohr magnetrons. So again, another treatment of the same experimental data on the supernova neutrinos and provide more or less the same upper bound on the level 10 to minus 12, and this comes from the demand of the absence of anomalous high energy neutrinos in the flux of that were detected as the supernova 1987A neutrinos. So now a few words about possible astrophysical bounds on neutrino millicharge Q. As you remember, it is not excluded that neutrino is an electrically charged particle. So in some generalizations of the standard model, as we have discussed on our previous lectures, it is possible that it may happen that neutrino are charged particles, but obviously, as we have discussed, this charge should be very, very tiny, and therefore we just call this electric charge of neutrino millicharge of neutrino. And again, these millicharged neutrinos can couple to plasmon, and again, in the process of plasmon decay to neutrino antineutrino pair, where this coupling is due to electric millicharge, again can set an upper bound for this charge that is about 2 10 to minus 14 charge of electron. That was obtained about 30 years ago by Raffelt and collaborators. So from the observational data of supernova neutrinos, much stronger upper bound have been obtained, 3 10 to minus 17 charge of electron, and the most severe bound comes from the demand of neutrality of neutron or neutrality of a hydrogen atom. So this is the most severe bound, experimental bound on neutrino millicharge, 3 10 to minus 21 models of charge of electron. And we obtain, together with my collaborators, the most severe astrophysical bound on neutrino millicharge. And I would like to comment on this bound, and would like to discuss now how this bound was obtained. So we consider general problem of neutrino motion in magnetized and rotating matter, something very similar to what can be expected to be found in the case of rotating neutron stars. Yeah. So, and we have found that, as I have announced already, that the energy is quantized, neutrino energy is quantized in a rotating magnetized star, not only due to possible electric millicharge neutrino interaction with the magnetic field. This is very similar to the electron energy quantization when the electron is moving in a magnetic field. This famous Landau levels of electron in a magnetic field. But also there is a quantization of the neutrino energy due to weak interactions of neutrinos with the rotating media. So we have solved quite a general problem of neutrino propagation in magnetized, this given by this magnetic field environment, and also accounting for weak interaction of neutrinos with the rotating media. This F menu stands for external magnetic field interaction of neutrinos, and F is proportional, determines the matter potential. And for F mu, we use the following expression. It means that we just describe the case when matter is rotating, and we suppose that the axis of rotation coincides with the direction of a magnetic field. So, and this is, again, we just used the method of exact solutions in description of neutrino propagation in such an environment, and it is possible to find the exact solution for the wave function of neutrinos, and also to find the exact value for neutrino energy for this case. So what about the energy? This is the neutrino energy. This is a scalar potential, electromagnetic potential that is not of interest when only magnetic field is present, and that is, we consider the case when matter is composed of neutrons. And this is the expression for the different components of momentum of neutrino. P3 is the momentum of neutrino along this fixed axis of rotation of matter and magnetic field. M is the integer number. Q is the millicharge of neutrino. B is the strength of the field. So the first part of the second term here, the second part of the third term, is just an effect of electric millicharge neutrino interaction with the magnetic field. It just exactly coincides with what we know for the electron energy in a magnetic field, the Landau energy levels. This is the mass of electron. This is momentum along neutrino, along the direction of the magnetic field. Gamma is proportional to the strength of the field and integer number. This is 0, 1, 2, 3, so on. So this is the Landau levels. So obviously millicharge neutrinos will also reproduce these Landau levels, but there is another term that also depends on the integer number. This is a Fermi coupling. This is invariant number density of background particles. In our case, we choose neutrons. And omega is the matter rotation frequency. So if we just switch off electromagnetic interaction of neutrinos, we get that the energy of neutrinos is quantized due to weak interaction of neutrinos with the rotating media. It's very, very interesting film, very new effect. G is proportional to the Fermi coupling constant divided by square root of 2. So this is a completely new effect, and also in this line it is possible to generalize if we just consider the quasi-classical treatment of these phenomena. We can say that in quasi-classical treatment neutrinos are moving in the presence of rotating matter on circular orbits. And just from this, and using the analogy with the Lorentz force, we can introduce the generalized Lorentz force, which in addition to electromagnetic part that is described by the electric charge interaction with the electric field and interaction with the magnetic field, an additional term that is due to weak interactions of neutrinos with rotating media. This is quasi-magnetic field, and this is a quasi-electric field that is proportional to the gradient variation of density along neutrino propagation. So it is possible to generalize the Lorentz force of electrodynamics for the case when neutrinos participate in weak interactions with the rotating media, and possible also with matter with non-zero gradient of the density. And so, implying these openings, we conclude we can estimate the characteristic radius of the trajectories, and just if we use the parameters peculiar to the rotating neutron stars, so we use the radius about 10 kilometers, the density of matter about 10 to 37 particles per cubic centimeter, and the rotation given by this 2 pi 10 to the third per second. So we get that the radius of the trajectories will be less than the characteristic radius of neutron stars for very tiny energies of neutrinos. And so here we can predict that rotating neutron stars can serve as a kind of filters for very, very low energy neutrinos, probably for relic neutrinos. This is kind of order of magnitude estimation based prediction of application of this phenomena. So, and now I would like to discuss directly the astrophysical, most severe bound, astrophysical bound on electric millicharge of neutrinos. So, as we have already recalled that if neutrinos are millicharge particles, and if neutrinos are propagating in a magnetized compact object, the trajectories will be modified, and the trajectories in general of motion of electrically charged particles in magnetic field are curved. So, and due to this, if we consider a neutrino escaping from a rotating pulsar, so they will escape the surface not perpendicular but with some inclination, and due to this there is a torque that is produced and given to a rotating star. So, and just a single neutrino generates a kind of feedback force, and it is possible to calculate the torque that is produced by one single escaping neutrino due to the curved trajectory of millicharge neutrino motion in a magnetic field, and just multiply by the number of neutrinos, we can estimate the total torque that is due to neutrino escaping from millicharge neutrino escaping from magnetized stars, and this should affect the initial star rotation. So we also estimate the change, the shift of the star angular velocity due to this mechanism. Here we just include both effect of millicharge neutrino interaction with magnetic field and also the neutrino weak interactions with the rotating media. But now we are interested in the first part of this contribution to the shift, and we just introduced the as we called it, neutrino star turning mechanism. So that is due to the following fact, that escaping electrical millicharge neutrinos, as we have just discussed, moving on curved orbits inside magnetized star, and due to the feedback on effective Lorentz force, the effect should disturb the initial star rotation, and we have estimated this shift of the frequency of rotation in the following way. This depends on the strength of the field, number of neutrinos, and just from very conservative demand that one should avoid contradiction of the impact of neutrino star turning mechanism on the observed data, rotational data on pulsars, we get immediately that the millicharge of neutrino should be less than something 10 to minus 19 charge of electron. So if you remember, this is the more severe bound in respect to other astrophysical bounds on neutrino millicharge. So, and this result is really is the best astrophysical bound on neutrino millicharge. Now, after this our discussion, I would like to announce some new developments in the theory of neutrino spin and spin flavor oscillations, and also that enable us to predict new astrophysical probes of neutrino electromagnetic properties. But I think that we shall stop here, and probably the last part of this novel I will give in the next lecture. Well, thank you very much.